Hello, everyone. Thank you for joining today to our 23rd session of Hackaday quantum computing class. As many of you who have been here before know that in September, we started the guest lectures. So as usual, I would remind people that all our content is held on Hackaday projects platform. If you search quantum computing through comics, you will find our class. It's been quite a lot of months that we've been doing this. Almost every Sunday, we talk about a new topic for 30 minutes to an hour. And we also have been using the quantum documentation from Microsoft and the quantum katas, where we had several classes that we did coding through the quantum katas exercises that we have at Microsoft. So as I mentioned, we have been having some guest lectures, and today we have Dr. Maria Schuld, and we have 2 more classes afterwards. And I think that would be probably we can wind down the class for this year. So let me introduce you Dr. Maria Schuld very quick. She is a senior researcher at Xanadu. I was actually lucky to meet some folks in Xanadu when I was in the conference Q2C. Very nice group of people there. They are a Toronto-based quantum computing startup doing some very exciting work. And Maria is also part of the big data and informatics flagship.
Well, hello, folks. I don't seem to hear anything. Is that typical?
Oh, you don't hear anything? What about others?
I can hear you perfectly fine.
Yeah, I can hear fine.
So other people can hear, so maybe it's on your side. Sorry. I'll move on. If you miss anything, we have recorded this. You can go back to it. So Maria is also part of the University of KwaZulu-Natal in Durban in South Africa. And she also is a author, not very different from the book I published, but Maria wrote a textbook, Supervised Learning with Quantum Computers. And she also has been working on the Pennylane software framework for quantum machine learning, which is a Xanadu framework using Python library. So we're very excited to have her here today. And quantum machine learning is definitely a very exciting topic. Both quantum computing and machine learning are developing fields. So it will be very interesting to see how these two fuse together. So before I give the slide to Maria, Microsoft also has a quantum machine learning library. If you go to the documentation, you'll be able to find it very easily in the Q# library list. So I'm super excited, interested to hear and learn from Maria today, and then look at our own documentation and compare the methods. Also a reminder that we just published a new set of learning modules on MS Learn. So this, I highly recommend everyone who's coming to this class to take these courses. These are for you to start practically using quantum computer. So we start with no prerequisites, and we have a learning path for you to get hands-on with the QDK and Q#, and gradually you build up your skills to doing some Groover search exercises. This is in addition to the katas we have been using, and this is a step-by-step course material that we curated, and we're constantly adding more materials. For any question about this class during the week, anytime, if you have questions, post them in the Hackaday project in the comment section, and also frequently asked the question, we record the class, and it will be on YouTube shortly after this class. Also, announcement for next week. So we were scheduling Professor Chris Ferry for October 25th, but then we had some schedule change, and 18th is open now. So I can't wait to hear Chris talk. So I asked him to come speak to us earlier. So Chris will be here on October 18th. And please note the time change is different from today. It will be later. So if you use Pacific time, it's 2 p.m. So please make a note of that. You will, if you show up at this time, you won't see anyone, but we gotta move it to a later time. So the topic will be on quantum tomography. And then the week after, on the 25th, we'll take a break. No class then, but then we'll have another one on November 2nd. All right, thank you, Maria, for joining us. I would let you take the stage.
Thank you. Let me try to share my screen. And if you can't hear me for some reason, if South African internet is too bad, then just let me know and we'll try to fix it. Okay, cool. You can see my screen, I guess, if you don't complain.
Yes, we see you now.
Great. Okay, cool. So first of all, thanks for joining. I was here already last week, Sunday, at like just 20 past 8 or something. I was sitting on my couch and I thought like, oh my gosh, I've got to give a talk now. And then I realized actually this week, which made me very happy. So I want to speak about quantum machine learning, being very cognizant that the audience might not be full of people who had quantum mechanics 101. And I guess from the course that you have seen before, what you expect now is me to go through an algorithm or two with lots of Dirac notation, lots of circuit diagrams, and convince you that quantum computing and this algorithm in particular can now speed up machine learning in some sense. And this is not what we'll do today, partially because my personal research over the last like 7 years or 8 years has brought me quite far away from this question of like, how can we speed up quantum, or how can we speed up machine learning with quantum computers? What I want to talk about is a question that the community has now, I mean, predominantly accepted as like a really, really interesting research question. And a lot of resources are like spent on this question, which is, if we take a quantum computer, a very generic quantum computer or quantum computation as a machine learning model, what happens? How can we train it? How can we predict with this model? How can we understand what actually mathematically is happening? So, so today, try to shade a bit your ideas of like always wanting speed ups. Today we're talking a bit more about like where does quantum computing actually fit into this big pipeline and this big market and this big theory and theoretical construct of machine learning. Let me just check. Yeah, what I want to convince you of, so my basic message is the following, and yeah, I try to explain this with not much math, and this is a bit challenging, but I hope we get it right, and we will see the comic that comes out of it. What I want to try to convince you of is that what makes quantum computing super interesting, if we understand it as a machine learning model, is that it's kind of a hybrid. It's something that is very similar to neural networks in that it's composable, it's a trainable model that fits into all the pipelines that, you know, TensorFlow and PyTorch and them have already built. But on the other hand, what's going on theoretically is very much like the methods that people analyzed in the 90s that machine learning has beautiful theory for. So this is the point I want to make. Check. Okay, cool. So we have to very briefly talk about machine learning. I just want to collect the things that I need to make this argument, basically. So machine learning to me always has 3 ingredients. Obviously, it's a big landscape, but I'm dumbing this down like into a few words here. We have data, usually modeled as a data distribution from which we can draw data. We've got a model. The model is the thing that actually solves the task that we want to do in machine learning. So for example, the model could be a predictor. It takes data points and it predicts, for example, if the data is a picture, it predicts what's on the picture. It could also be a generative model that doesn't necessarily take inputs of that form, but they produce data. It could also be a translation system, whatever you want to make it. And the third ingredient is a cost. And the cost is basically a function that measures how well does the model do on the data. The cost is also like a whole, modular thing that you can change. You can analyze what different cost functions do. You can construct the cost with different terms, regularization. Like those of you who work in machine learning know the pain of this. So now, what is the task in machine learning? And I think in early quantum machine learning, we, or like a lot of people in the community, got this a little bit wrong. The task is use data samples, so examples, a small example set of data to construct a model that minimizes the cost on unseen data. And this is important because what we got wrong, or what many people get wrong in quantum computing when they just start to engage with the topic, they think machine learning is to use data samples to construct a model that minimizes the cost on the data samples. So on the small data set, on the training set that I basically get given. But the task of machine learning is not the optimization itself, it is the generalization afterwards. So you want to build a model that does not necessarily only perform well on the data you have, but it has to perform well on data you've never seen. So if you've got a translation system, if you train it with 200 words, you want it to also start understanding language that it hasn't heard, or even a language it has never been trained on. So generalization is like the big thing. When you open then a textbook, like the beginning is always like linear models, although linear models are something that we know from statistics and also in physics like for hundreds of years. But however, even if you go to proofs of hectic deep learning models in crazy papers, often people actually go back to the linear model. So they're quite a fruit fly example for machine learning. What happens here, I probably don't have to explain to many people, is like that linear models basically just think of a mathematical function that takes the input, think of it as a big data vector, and multiplies it with a weight vector. And this weight vector can be trained or can be chosen. And what happens basically in the space of data here, we now have just two-dimensional data. So think of this as being 2 pixels of an image. What this linear model will do, it will create a linear decision boundary. So everything in the data space that's on the left side of this hyperplane, in higher dimensional spaces, will be, for example, classified as one class if I put a step function on the result of this model, for example, and use this for classification, and the other thing will be classified as the other class. So now what's the important point here? Those of you who have worked with linear models before know that if I want to optimize a linear model, I have a really beautiful and very simple optimization task, which is convex optimization. So without like going into mathematical details here, convex optimization, you can simply think of an optimization landscape, something where you want to find the minimum, where you have a global minimum and you don't have local minima. So basically, if you go down, you will always like kind of find your beautiful global minimum. And what you can also do is you can find an equation, so a closed form equation of this W vector here that optimizes this model. So basically, theory is very beautiful. Computationally, it's so and so. So this closed form equation you can solve on a computer quite nicely. However, the way to solve it, for those of you who remember it, is that you construct a big data matrix out of your data, and then you have to invert that matrix. And matrix inversion is, it's efficient, so it has a polynomial runtime algorithm, obviously, like quadratic in the number of data, or a bit more than quadratic, actually. But for machine learning standards, like being quadratic in the number and size of data is actually quite big, especially when we go to bigger data. So how did machine learning solve this? And I still need like all of this narrative basically to like say where quantum computing fits in. Oh, sorry, not how they solved it. They haven't solved it. That's the wrong line here. What I want to say is, so now we obviously have a problem that linear models can only classify data in linear decision boundaries, so they're rather stupid models, so they can't do very much. People have figured that out probably in the 40s and 50s. It was the famous XOR problem, if people remember. And but what happens is that you can actually give this very simple model a lot of power by mapping the data with a linear map into a really high dimensional space. And that means that in your original space, you can actually have models that are more complicated, which means decision boundaries, if we think about classification for now, that are very complex. The beauty of it, we're still doing convex optimization because I don't have a nonlinearity in my data. So this means we are doing this convex optimization in a very, very high dimensional space now. And this high dimensional space, in this high dimensional space, we're still doing something linear, but in the original space, we're not. Now, computationally, we're now doing something, that was already not so easy, and now in a really high dimensional space. So we're actually getting more and more problems. And the beauty of kernel methods in the 90s, I won't go into why they're called kernel methods, it's a bit more complicated, but is to find out that actually this convex optimization problem can be solved in the original space. So I don't have to go to these very high dimensional spaces. It's just a mathematical construction. In the end, I can do all my computation in the original data space. So to summarize here, we made a more interesting model, a much more interesting model, beautiful optimization, kind of easy to solve, I still have this problem that it's quadratic in the number of data and not linear. So yeah, doable, but maybe not optimal or not like super cool. So there's still bottlenecks. And now the last step that I need here is now deep learning. So this was basically the thing that took over from kernel methods, maybe from a similar paper like in 2006, but probably 2010, like things started to get rolling properly. And what we have here is usually also quite a particular type of data. So we've got big data, we've got lots of data. We often have data of a specific kind. So deep learning started off with image recognition, which was the first problem it really solved. The models that we use are, well, most of you know they are neural networks. So they are basically produced by taking this linear model and now taking the nonlinearity out of it. So basically now we are nonlinear also in the W. And then we compose this block over and over again. And so I actually don't even have to talk about deep learning by saying something about neural networks. I mean, most people do, but what makes deep learning so crazy or so cool is that what it uses as models is a model type that's composable. So you can stack them, you can make an image recognition system, stack it to a translation system, and do crazy, crazy things. And the model is differentiable. Okay, I have to explain this. Like, what I mean by differentiable here, I mean, models in some sense are differentiable if I can compute how the output changes with respect to parameters. So in this case, like here, these W's. But what I mean here is actually that it's very efficiently differentiable. And this has been termed backpropagation in neural networks. So this just means there's an algorithm that can really, really efficiently like optimize these models. And this algorithm is in general a gradient-based method, so a gradient descent-based method. Why do I need this like really good optimization method, and why do I actually need gradient descent here is because this nonlinearity switched now and it includes the weights. We now don't have this beautiful convex optimization problem anymore. We have a very difficult non-convex optimization problem. If our data is very high dimensional, we have a lot of weights in our model, it's a really, really hectic optimization problem that's non-convex. Non-convex for this talk just means difficult. And now what enabled deep learning really is this type of model. This type of algorithm to optimize this model, although the cost function looks really horrible, the landscape is really horrible to optimize. But also these two things here, which is high performance hardware. So we're talking about GPUs, we're talking about big high performance computer. So also like server farms that sit somewhere and optimize your models. And what really also enabled this field is special purpose software. And I'm talking here about the likes of TensorFlow and PyTorch and MXNet and JAX or whatever you want. This is software that is written to basically compose models that are end-to-end differentiable and then differentiate them. So basically, you just have to write an algorithm, which is your model. You can write also a cost function on top. You write like your entire algorithm in a language such that your computer knows exactly how to compute derivatives of any parameter you used anywhere in your algorithm, of the output with respect to any of those parameters. So this is what makes deep learning successful. Oh, by the way, and people are wondering at the moment why this whole thing works. And the only thing in the last few years that people can say really is it's an interplay of all three methods, all three things. You have to have the data, you have to have this type of model, and you have to have this gradient descent algorithm. You can't really make up a theory that only depends on one of them. Okay, cool. Now, okay, I've spoken a lot about machine learning, but how can actually quantum computing help? And again, there are lots of different ways. So for example, the first like ideas, maybe in the 2000s, were thinking very information theoretically about this. For example, and there's a beautiful review summary of this work, is like maybe if you had kind of quantum oracles, maybe you could have, you can do something with query complexity. I don't know if you've heard this term, but what it translates to in machine learning means I don't have to query my data oracle very often. So maybe I can learn from fewer data samples. There's also, since the beginning of quantum machine learning, which is a term that has been only used probably for 5 or 6 years now properly. I mean, before it was more like scattered papers that looked into this. But there's also this like kind of idea to process quantum data. Kitty and I were chatting about it a bit earlier. What I mean by this, quantum data is a word, people use it for lots of different things. But what I mean by this is have actually quantum systems that carry quantum information and use now a quantum algorithm on them. For example, a photon, send it into a quantum computer that's photonic and start experimenting with this data and start to analyze it. And why I put here as a reference folklore is lots of people talk about this all the time. It might be the coolest application of quantum machine learning. There are some papers that also like, have some ideas, but I think something that is really like proper. So this path is not really gone yet, I think. Okay, second idea, the cost side of things and the optimization side of things, we can try to improve it. And that was the beginning of quantum machine learning a few years back. People tried to basically just speed up the optimization part. So, for example, this paper here was one of the very first one. Nathan Bieber also like worked in the Microsoft group for a long time. And so he just took a linear model. You remember the matrix inversion that I was talking about, and did it on the linear model. The second paper took the second model, the kernel method, a very specific one, a support vector machine, and did the inversion problem here also on a quantum computer, or proposed algorithms that did that. Using, you might have heard of these, like these HHL type algorithms for matrix inversion. There's a lot of controversy here because some of these algorithms use techniques where you need oracles for data loading. So if they can really speed up things exponentially, like claimed in the paper, is very tricky to tell. And it's hard in machine learning because we don't only want things to be fast, we want them to make sense and be useful as well. And this usefulness is very hard to quantify scientifically. And then I also put like another early idea here to use quantum annealers to train a model called Boltzmann machines. Another one, I just put this in because I find this really fascinating, but I don't know a single paper that has really thought about this. Maybe there's also quantum computers could find better solutions. And better solutions are solutions like models in the end that generalize better. But I haven't seen like structural work on this. Tell me if you have. I want to talk about this one here. So we tackle the model. And obviously, again, like everyone in quantum computing loves thinking about speed ups. So you can think of like, let's speed up existing models. So there were lots of early papers. There are really a lot of papers on this. So this is just a very random selection. And the one I want to speak about is actually now, as I said, not how can I take a neural network and just make it faster. I want to actually talk about how can we design, or how can quantum computing give rise to a completely new class of models? If we understand it as a model, a circuit, what model is that? I think the first, okay, you can never say the first, but like the first time I've seen this type of thinking is in this paper where someone said, if a Boltzmann machine is something like an Ising model, which is like a typical physics model, and we have quantum Ising models, why don't we just invent quantum Boltzmann machines? And then the second paper here is a summary of this approach that I will talk about now, or a review paper on that, which is this idea of using a certain type of circuit. Okay, now so the rest of this talk, I will just draw this argument now. Why are quantum models interesting, or quantum circuits interesting as models? So first of all, there's a realization, there is a certain type of approach to quantum computing that comes out of NISQ devices, so the devices that we use at the moment, that was basically born out of desperation because they can't run any feasible algorithms, not even like 20 gates, and then the noise just drowns everything. So the idea, and it came very much from quantum chemistry, is why don't we just like train our circuits, a bit like in quantum control experiments when we have feedback loops to find good gates. Or so the idea here is take a quantum circuit and just make a couple of gates trainable, so have them depend on parameters. And this whole approach to quantum computing is called variational circuits. So now the idea of using a variational circuit as a machine learning model is absolutely interesting. Because why? Because they are composable and differentiable, and I will tell you exactly why in a few seconds. But this means that we can actually just plug them into the entire pipeline of deep learning, because we can treat them like neural networks. We can do gradient descent on them. We can, so the hardware we're building is like actually the quantum hardware here, but we can also make use of the special purpose software. So we can build libraries for quantum machine learning that plug into TensorFlow and PyTorch and just extend them by quantum computing. So this idea really makes quantum computing ready for machine learning on a much bigger scale than just coming up with, I sped up a support vector machine. This is like a very big way of thinking about quantum computing and machine learning together. Let me tell you why I say that these variation circuits, which are just these trainable quantum circuits, are composable and differentiable. The composable part is probably quite easy to stomach, because already you know that quantum circuits are composed of gates. So we can just stack gates, or we can repeat a subroutine, or we can branch out with a subroutine. So, like what we do in circuits is we compose circuits. So that's maybe not so difficult. But why are they differentiable? And this is, actually not so clear in the first moment. So let me try to explain this here. So this is a circuit diagram of, just a typical variational quantum circuit. If I have an input, I encode this input first. So this is this idea of state preparation in traditional quantum computing. Then I've got a couple of gates. Some of them depend on parameters. I use the same here. This has no meaning. I just didn't want to clutter things. And then I measure. So if I now plug this into TensorFlow, into a machine learning pipeline, the machine learning pipeline will go to this computation at some stage and ask, I want to do gradient descent. I need a gradient of your computation. So I need to know what's the partial derivative of this output here with respect to any of these inputs and these parameters here. But it's not, you can write this down on paper, but it's not entirely clear that these partial derivatives are things you can actually compute on a quantum computer. And this was kind of like a whole kind of idea or question that a lot of papers in succession worked out more and more and more. By the way, these two references here are just from, basically this was actually a paper from my time at Microsoft, just in reference to Kitty. These were kind of, as far as I understand, the first two papers that had this idea of using quantum circuits in machine learning in this way. So I put them here. But now back to differentiation. So there was a whole string of research that showed that if we put a quantum computation as part of a big computational pipeline, that at some stage asks for gradients. So the quantum node, I call now the quantum computation, has a forward mode. So it just like makes the computation and sends it further. We can show that if it gets asked for gradients, that the same quantum node just makes a computation twice. And it shifts the gate where the parameter enters with respect to which I want to differentiate. It just shifts it once to the one side and once to the other side. And then it takes the difference between these classical outcomes of these circuits. An outcome of a circuit for me is always an expectation value. So physically, this means I run my circuit a lot of times and then I take some average. So it's a number basically. This looks a bit like finite difference rule, if you can still follow, but it's actually a macroscopic shift. So this depends on the gate, what the shift is. We don't know if every gate, quantum gate, has a shift, but the common ones have. But this allows us to basically, by just running the same computation twice, to get a gradient out of the quantum node. And this allowed us now to compose software. So, for example, Kitty was saying I'm involved in like developing a quantum machine learning special purpose software called Pennylane. And the idea of this quantum software, as I said, is really to plug into machine learning pipelines. So on the left here, you see code written in PyTorch. It could also be TensorFlow or even NumPy. So there are different ways you can do this, where we just exchanged the model with a Pennylane, a quantum model, basically. And so you see, you can use the entire optimization pipeline here, written really in PyTorch, but what you optimize is now the quantum model. So we don't have to invent the wheel again. We just use deep learning to optimize our models, which is really, really powerful. Okay, and now the last little argument that I want to give you, and this is a bit, maybe my colleagues would stop here and go into another direction. But what I find extremely interesting is the following observation. Let us say now, we just like do something like a Gedanken experiment. So we just like play a bit around here. We had this circuit here that was the variational trainable circuit in the middle. But now I interpret this circuit by just like changing my measurement. And this is like actually something that happens in the lab all the time. When you do a measurement, you write it on paper as an M, or it's an operator, it's an observable. But in the lab, you probably have only a certain type of measurement that a computer can do. And how do you make a different measurement out of this very simple measurement is you just apply a circuit before and some post-processing probably after. So the circuit before the measurement can be interpreted as changing the measurement basis. So I kind of like just call this entire like purple thing that I had before just M. But if this circuit is trainable, it's actually now the measurement is trainable. And why I'm doing this is because now my algorithm only consists of this. So this is my machine learning algorithm now, right? It consists of data encoding and a measurement. And now let us try to, I'm just giving you a picture because I wanted to avoid too much maths, but what is a data encoding and a measurement actually doing? Data encoding basically takes classical data, for example, an image, like all the pixels of an image, these values, and maps it to quantum states. So it maps it to a very high dimensional space somehow. And the measurement does something that is very similar to a linear decision boundary, actually. So, and from just this image, you will remember like the image before of the kernel methods, where you said like we map data into high dimensional spaces and we do something linear and something very simple. So linear, there's like the terms and condition come in here. There's a quadratic factor somewhere. So just like if you are very pedantic, like you will immediately shout. But still the maths that's going on here with state preparation and measurement is very, very similar to these kernel methods. And so let me just go back. These two papers came out. So this one is from us, from Xanadu. This one's from IBM. Came also out in very close succession, and noticed that actually these data encoding things in a quantum computer are basically just a feature map into a high dimensional space, and then we can, apply the entire apparatus of kernel methods here. And this is how I want to finish. And so, as I said, this is like kind of the argument I want to give why quantum computing is really interesting, and is more interesting than just speeding up machine learning as we know it. It can actually create new things. And just to summarize this argument again is, if we take this variation circuits as models and we interpret it as just like, we map data, to a quantum state, and then we perform a measurement. And the measurement, or even the data map actually, both can be composable and trainable. That means that this model is now in the framework of deep learning. So we can use all the ideas of non-convex optimization that I showed you with Pennylane. But it is also a model that has the whole theory of this very beautiful convex optimization. So we're basically non-convex optimization is just like think of it as a lazy proxy that we use because we don't know about this theory yet. We just close our eyes, there's a black box, we just use it. But if we use this theory of that this model is actually a kernel method in some sense, we can start thinking about how can we utilize these ideas of convex optimization. And maybe the last thing, and this is maybe more for people who are a bit of experts already in machine learning, this idea of doing convex optimization and just inverting a matrix, a specific matrix. So this was this trick that people used here to still keep on doing convex optimization and tractable on your computer. We can do this with a quantum computer, not in quadratic time. This was this problem that we before had. If we have big data, quadratic time and the number of data is really bad. But on a quantum computer, we can do it in linear time. And maybe this closes a bit the circle of why personally I stopped being so interested in like only having exponential speedups everywhere. Because if we can just invert a matrix in linear time instead of quadratic time, we remove one of the biggest bottlenecks of the methods in the 90s from doing something like with big data. So we really have a model that can do both, or is a hybrid of the two. Yes, and I think this is where I finish. I hope I haven't stepped over my time. And if you have questions, I'm very happy to speak to you about.
Thank you very much, Maria. Is it possible to kind of quickly show us how Pennylane works?
No, that's not a problem. Let me stop sharing quickly. And just like,
and
take a new tab.
Feel
and then
free to post your questions in the chat or unmute yourselves if you have any questions.
Okay, 1 second. Cool. I think you can see now my entire desktop. So, this is Pennylane. This is the landing page. Oh, sorry. Yeah, cool. Yeah. Very briefly, if you want to learn more about this way of thinking of quantum machine learning, you find a lot of resources on the quantum machine learning tab. So my internet seems to be slow if it does a lot of things at the same time. Okay, that's a lot. So especially what you find there is a lot of demos. So what we're trying to do at Xanadu a lot is, because what we want to do, we want to get lots of people ready to play with this, right? So this is the idea, give it into the hands of the community and see what they do with it. So what we're often doing is we kind of like, so we have got like basic introductions into quantum machine learning here in code, but we also like code up a lot of research papers. So if someone comes up with a research paper, we kind of make a tutorial about it so that you can actually implement it in Pennylane yourself. Secondly, what I want to show is Pennylane is not itself something like Qiskit or Q#, that it's its own language only, but it's more a manager of languages. So it can actually, it uses for quantum computations either its own simulators or a lot of devices. So, and you see here, we even have a Microsoft device. So what happens is Pennylane says, okay, I need this computation. It sends it off to, like your local Microsoft installation of Q#, or maybe a hardware device. So it can also run stuff on hardware. It gets the results back and then processes them. And then lastly, here you find the documentation, which is, gives you like kind of an introduction of how the language works, since there are many. Yes. And if any one of you is from the Microsoft community and wants to help us to develop the Q# plugin further, because I think it's, it has been coded up like a year ago, would really like to update it as well with the latest stuff in Microsoft, in Q#, then just let us know. Cool. Let me stop sharing.
There is a question in the chat. I guess, Maria, you also have already put a lot of papers in your presentation. So this one is asking if you have any recommendations of papers related to QML.
Especially in the optimization section you mentioned, yeah. I would go. So maybe I should actually not have stopped sharing my slides. That was a bit stupid. Wait 1 second.
And afterwards, you can also send me the slides, and I will be able to upload it to the Hackaday page, so people can also look at the reference.
Great. The only thing I wanted to quickly say is, so this one here, in my mind, so Patrick, Reventos, it was Lloyd, and Mussini was like really kickstarting quantum machine learning for the first time, and that had this idea of doing the inversion really fast, like based also on ideas that have been developed here. So look at this paper and what gets cited here, and you find a whole string of ideas who have like more and more elaborate ideas of like this exponential speed up claim of like matrix inversion in one place or the other. And then, as many of you know, there was a bit of a community shock, because then a couple of years ago, a young student came, Evin Tang, and she just dequantized some of the algorithms, not all of them, and showed that actually if there's a quantum exponential algorithm, exponential speed up, we can also find a classical algorithm that has the same like input oracle. And you can also send me an email at maria@xanadu.ai. Then I'll send you an overview paper of this type of work. And then lastly, what I want to say, the other strain of optimization was a lot with quantum annealing. You find a lot of quantum machine learning in early days on quantum annealing. And there it's always a bit tricky, obviously, to have proven speed ups. So there's a lot of experiments there. Yeah.
Thank you. I see Simon has a hand up.
Yes. Good evening. Maria, I have a question regarding Pennylane. Do you hear me?
Yeah.
Yes,
okay.
I hear you.
Yeah, sure. So the goal of Pennylane is to design or achieve a common, let's say, standard framework to enable to bind all the dots between the different frameworks that currently already exist on the market, including SharpQ or Torch or all the, let's say, the others that are currently on the market. This is the original purpose behind the Pennylane.
Yes. So yes and no.
Okay.
Yes, you can do everything in Pennylane with a native framework. So you can. So I don't know if you see the slide here, but where you change the device or what's the backend that actually does the computation. If it's a hardware device or software or like a simulator, is changed here. And you see there's a default qubit. And we've got a couple of default devices that ship with Pennylane. So Pennylane also does the quantum computation if you want. But if you want to use something else, because you want to use Google's new hardware or whatever, I don't think it's like public yet, but like you can connect to those as well. And then on the other side, there are the machine learning frameworks. That's PyTorch, TensorFlow, and we've got AutoGrad, which is a NumPy extension to do this like kind of machine learning stuff. So there you also have the choice to use those three. And the easiest one is NumPy, and that just looks like plain Python. So you can use Pennylane without ever knowing about anything else than Pennylane, but you can also use it to connect. I hope that helps.
Yes, thank you so much. Thank you so much, clear.
Cool.
Another question in the chat: how is the quantum memory being thought of in terms of old explosion of learning for a general purpose AI or NN, because that's neural network, because that's where I see its biggest impact. Any thoughts?
Okay, that is a bit. What do you mean by quantum memory? So quantum memory could mean a quantum system that stores data as quantum information. And in that case, obviously, that is actually our sore spot. So this is like not very clear why this is an advantage, because so first of all, you have to always take the data and load it into quantum memory. So you already create an overhead, even if you can then read it out of that quantum memory very quickly. But I'm not too sure if you're talking about a different use of the term quantum memory here. Maybe you want to unmute yourself and ask.
Yeah, do you want to clarify a bit? Maybe their microphone's not working. Can't really hear them.
Hi.
Hi.
Oh, yes. Yeah.
I'm from Canada, and just to give a little background, I'm a blockchain developer, and there's been a huge buzz in the whole mining faction to use quantum computing. So what are your thoughts on that? And because basically, if to give it to you in like 30 seconds, they use huge GPUs to basically solve an algorithm so that they can go ahead and get a reward. So how do you think this will affect that, and do you think it'll help in any way or form?
Yeah, I think I'm not qualified to speak about this. So, but one of my students, she's really into blockchain, and she gives me like a lot of information on this. And as far as I understand, you're obviously, and I'm sure people are doing this, right? You have to find an algorithm like that you can do this mining with, where you have like the right balance of like hardness and but still get rewards, or like I don't know what you get in, and then prove all the the hardness proves that like that this can't be cracked and stuff like that. So I really don't know. I'm sure there's a very active community. So I think anything computational you put quantum in front of, you will find this community. But I wouldn't know this. I'm sorry.
No problem. Thank you so much.
Next question actually relates to a question I had. So they're asking if Pennylane has any interface with D-Wave quantum computers, and it also deals with optimization, which potentially help in cost reduction. So I had a similar question. Is like the other place I heard about optimization and lower cost is quantum annealing, or generally speaking, quantum inspired optimization. So it's different method, but then is there any relation between them, or if not, how are they comparing?
Yes, so no, Pennylane doesn't have an interface to quantum annealing yet. At the moment, it only has two computation models that it supports. The one is circuit-based quantum computing, so the normal ones, with qubits. And then it also supports continuous variable quantum computing, which is something we're very actively investigating at Xanadu. Photonics is very natively written in that language. But at the moment, we don't have plugins to annealers. This might be a question of time. I think why it's not a priority at the moment is that although quantum annealing was really important, actually even D-Wave themselves with their research team were very important for the early days of quantum machine learning. People have gone a bit away from this, and I'm not entirely sure why. Maybe it's partially because it was so hard to prove that things are better. So people still do a lot of experiments like on D-Wave, but also obviously because the D-Wave is solving a very specific problem, which is the quadratic unconstrained optimization problem. Although you can put machine learning into that framework, it's not a very native one. So if you think about deep learning doesn't necessarily want to solve that particular problem. You have to kick it quite hard to get into that shape. So I think that for some reason in the community, interest has dropped a bit in that. So this is why probably we don't have it. But if something interesting pops up, then we easily extend it that way.
Yeah, we have a very big effort on quantum optimization or quantum inspired.
Yeah, that's also true. But then obviously for you need no quantum computer. Yeah. So then. Yeah,
that's the fun thing about it, is that you can improve classical algorithms and run on classical hardware.
And this is also why I'm sometimes not, why I'm not even so bothered about speed ups, because just this way of thinking about computation is so different, and it really opens like a couple of doors. Also to think of a computation that's probabilistic by itself, right? Like it's, like quantum computing, the one thing that I wish someone would have taught me right from the start, I would have understood it a lot easier, is that it is not the same as deterministic computation. What you get out is a probability distribution. And especially for machine learning, this is super interesting because a lot of machine learning is in probabilistic theory. And
yeah. So in terms of the quantum memory earlier, Sumit means some general purpose AI in terms of data explosion.
Okay. Yeah. I mean, well, it depends a bit also on how you formulate your problem, right? If you have this interface, or if you have a data set that's classical, and then you want to feed it into a quantum computer. So this is this kind of like big controversy about the early like speed up algorithms of this matrix inversion kind. Is like colleagues always said, yeah, but I can invent this, like I can assume this oracle that just picks data super efficiently somehow. But in my mind, if my problem is formulated as given a classical memory with classical data, the first thing I have to do is touch all my data. I mean, I can subsample, but then I don't have the original data. I just have a subset of data, right? So I will always have to like take all my data and load it into something. Once I've done that, I already have an algorithm that's linear in the time of the data. So I won't get an exponential speed up. And neural network training is linear in the amount of data already. So I find it very hard to argue like that if you formulate the problem this way, that there's a speed up. The moment you have quantum data, so you already have a quantum experiment and then you get quantum information out somehow, then immediately you have the speed up, but then you don't even need a paper about this. This is like follows trivially. Yeah.
Another question with regards to nodes in neural networks, how do you see this playing out in future as individual quantum nodes, specializing in specific feature or same as classical?
So there's also here different ways where you can plug your quantum algorithm in. You can throw away the entire neural network and replace it by a quantum algorithm. Or as you say, if you talk about nodes, you probably mean neurons, or I don't know if you can think of a neuron as a quantum computation, you probably could also. But what people do quite a lot is they take a layer out of a neural network. So for example, and then replace it by quantum computation. So for example, there are experiments, actually, if you go to Pennylane and you look at the transfer learning tutorial, there's one like really very popular tutorial, where you take ResNet, which is an image classification neural network. You can take it preloaded, download it from, I think it's written in TensorFlow, and then you just chop off the last layer and replace it by a quantum circuit, and then you see what happens. And so this is since neural networks are modular and quantum computation is modular, you can really like start mixing and matching quite interestingly.
Cool. Guess let's take the last question. Is more not about the technical, it's more about how much you would need in terms of quantum computing, quantum physics for one to know to use QML.
That's actually a nice last question. I'm a bit biased here, and also colleagues would answer this differently. I personally think the less you know, the better, because everyone who's in quantum machine learning comes from quantum physics. And we have these old ways of thinking that have been practiced in the last 30 years. And I think what you really need to be good at is machine learning, because the quantum part, you could probably learn quite quickly, because we're talking about these very generic models. You don't have to know anything about implementation. You probably don't even have to know about noise models or something like that, just to like understand the basics. But since actually this question of generalization is really actually very non-trivial, there's a lot of theory about this. When does a model generalize? I think this is what we actually start to get skill sets in. So yeah, I think you don't need to know too much about quantum computing there.
Great. Keep an open mind. Okay, so let's call it a day. Thank you so much, Maria, for joining us. It's also your evening now, so I hope you enjoyed this as well. Okay, thank you everyone for joining. I did take notes, but
Yes,
not
very
a lot
much.
of
Thank you very
drawing.
much.
Didn't do a lot of drawing today, but I will try to make something to post next week.
I'm excited. I'm looking forward to what's coming out of it.
I need to first convert some of the functions into cats.
Yeah. I didn't mention much cats actually. Usually people do machine learning on cats and dogs, but even
That's
that
true.
was replaced by ants and bees. So sorry about that.
That's a good inspiration. I'll try that. Thank you so much for joining us, Maria.
Okay. Have a good
Talk to you
evening.
next time. Bye. Thank you, everyone.